We continue. So this time we invited Professor Mythily Ramaswamy from here, ICTS, who will talk about some fluid models and their control aspects. Thank you very much.
Yeah.
Please.
Yeah. Thank you. Thank you. Let me start. I'm sorry for the last lecture. You probably are too tired. So it's not going to be very technical, and I'll try to make light enough talk. Okay. So I've organized it through some description, and then what, as an analyst, what we do. And I have two topics. One is fluid structure interaction problems, and one some control questions of these fluid models. So many natural and engineering processes are modeled by PDEs, which you know already, you would have studied: heat conduction, diffusion of chemical, vibration of string, potential flows, all these linear equations, and many important nonlinear equations. We saw in the morning Euler and Boussinesq fluid models, and these are very important in atmospheric sciences, oceanic sciences, aeronautics, and blood flow. So the common fluid descriptions are often used are due to Claude Louis Navier, who was in this late 18th century, and Sir George Stokes in the early 19th century. Then the incompressible Navier-Stokes with the divergence free velocity and with constant or homogeneous density. This is one possible description. Or you can also consider incompressible Navier-Stokes with divergence free velocity, but with inhomogeneous density. The density is not anymore constant. Or you could also consider compressible Navier-Stokes with evolving velocity and density. These are the three popular models usually considered. So I start with this one model. This is incompressible divergence free velocity with, and constant density. So I have usually for velocity and pressure P of the fluid, we derive it using the conservation of momentum, that is Newton's law. We will use to compare the forces, and you can write down this equation where nu is the viscosity coefficient, and we take the divergence to be 0. Now when you look at the analysis of the PDE problems, first we would like to know whether the PDE is well posed. That is, it has a solution, if this is unique, and if the solution is continuous with respect to data. So these are important for the problem to be well posed. And this is very well known in the linear cases, but in the nonlinear cases, many questions are still open. Main one is Navier-Stokes, as I will find out. I'll show you in the next slide. So after you settle existence and uniqueness, you see qualitative properties, various estimates or limiting behaviors, and also control of solutions. Like the talk we had in the morning, there were a lot of estimates and the limiting behavior. And so it's similar, similar questions can be asked. Now, but we have to be clear what solution we are talking about. The solution itself, there are several concepts. So the often used classical solution, a function having as many derivatives as required for the differential equation and satisfies the equation pointwise everywhere in the domain. This is the smooth function. Or we could also look at the generalized solution in contrast. It satisfies PDE in an integral sense when multiplied by a smooth function, or we call it weak solution. So we use the theory of distributions introduced by Schwartz that provides a very nice framework for generalized solutions. So very often used method is you look for a generalized weak solutions and then obtain regularity estimates. And finally, if possible, conclude that the solution obtained is indeed a classical one. So what happens with the Navier-Stokes? Leray used long back, 1 century back almost, used a compactness method to produce a global weak solution of the Navier-Stokes equation. But in 3 dimension, it is still open because the uniqueness of this solution is not yet known. Or if you can always prove there exists a unique smooth solution for small data or in a small time interval, that can be proved. But it is not known if this smooth solution will extend globally or develop singularities. So that is why the Clay Mathematics Institute has posed this millennium problem to decide if there exists a smooth global solution for reasonable initial conditions, or there exists initial condition if there is a blow up. So that is still not settled. So what do we do then? We use the solution where whatever exists with constraints and work with that. So we work with fluid structure interaction problem, or as well as the control problem for Navier-Stokes. But so I'll briefly indicate what kind of fluid structure, why they are important. There are some macroscopic models as well as microscopic models. So you look at birds or aeroplanes, they are moving in air. Air is the surrounding fluid. Or fish and submarines moving in water. Or microscopic models are ciliates and flagellate, which have very thin cilia, which they keep moving. And so these are some models which they use self-propelled motion to move in the fluid, or fish swimming in the fluid. So there is a self-propulsion mechanism, that is a body generating a non-zero flux through the boundary, or a mechanical pump sucking fluid in front and expelling at the rear, or you could be a tangential motion of the boundary of the body. So, or you can imagine a system of moving belts located on the body. So this kind of self-propulsion mechanisms can be imagined. So we wanted to set up a mathematical model with suitable boundary condition and prove the existence of the solution to that system. So now you combine the fluid with something for the solid. And so I'll try to describe briefly the rigid body that is moving in the fluid, and I'm assuming it is self-propelling. So you can imagine that is occupying, the solid is occupying some domain ST in R3, 3-dimensional domain, a closed bounded simply connected rigid body, and its center of mass is HT, and it has linear velocity and angular velocity denoted by H prime T and omega T. So the total velocity denoted by US is the linear plus angular, the vector product of this with x minus ht. These are all R3 vectors. So that solid domain at any time is given by this. This is the center of mass plus the qt is the rotation, because the body is also rotating in the fluid, times y. Y is the initial position of the body, s naught, that is what is denoted. Okay, so the point is this domain is moving in the fluid. Rho s is the density of the rigid body, but the total mass is constant in time, denoted like m. Now I have to write down the equations. They will come from conservation of linear momentum and angular momentum. So first we define the moment of inertia Jt. So the Jt is a standard, so we can write down in this way. So this is again Newton's second law. So mass into acceleration gives me the total force. The total force comes from this is the Cauchy stress tensor. So that is acting on the surface of the body. That is what we are assuming. And similarly, for the angular momentum, I have the Cauchy stress tensor again acting on the surface of the body. So this will be the equation for the body. And I already showed you the Navier-Stokes equation. So the combined one, will there be a solution? So that is what our problem was. So the earlier work in incompressible homogeneous fluid, so they could get weak solutions for fluid solid system, but that was with homogeneous condition, that is, and with slip conditions in a bounded domain or Navier slip condition in the whole space. There were also some results in self-propelled motion, but in very, very special symmetric situations. So what we wanted to do, that is with my collaborators, Sharka Nechesova, Arnab Roy, Anya Schlomer-Kemper, we wanted to study a rigid body self-propelling inside an incompressible inhomogeneous fluid. So the fluid is, the density is also varying. So for interface condition, we wanted to try Navier slip condition for the normal component and self-propulsion through the tangential component of the velocity. So most of the fluid structure interaction problem is the body is moving. So it is a moving domain problem in an inertial frame. So we'll have to do change of the frame and then set up a framework on the body and then rewrite the system. So there is technically it's quite complicated, but you can overcome. So our final result was a global weak solution in the whole space, but it's only a weak solution in a suitable Sobolev space. I don't explain the details here. Then we wanted to consider for the compressible fluid. So the earlier work for rigid body inside the compressible fluid, I wanted to recall. First of all, it was Pierre-Louis Lyons who introduced the notion of renormalized solutions for compressible fluid systems. So then that has been extended to many other cases which was not covered earlier by Pierre-Louis Lyons' theory. Afterwards, people started looking at fluid solid system, but usually with Dirichlet interface conditions, because if it is Dirichlet interface, across the solid boundary, the velocity will be continuous and it's somewhat easier to proceed. So we wanted to try with the Navier slip condition, in which case only the normal component of the velocity will be continuous across the solid boundary, but not the tangential component need not be. So that posed a lot of problem in addition to the earlier problem of moving domain in an inertial frame. So we had to use very carefully the weak solution definition and construct test functions around the solid boundary, which will match the discontinuity in the velocity. So with that, we could prove, but only local in time weak solution in the whole space. We could extend it later to several bodies in fluid, in bounded domain also with mixed boundary condition. So this was quite technical, so I didn't want to include the details. But let me move to the other topic, that is control of differential equation, which how do I remove this in the computer? Okay. Yes. Okay. So the control of differential equations is also a very important topic in the applied field. Engineers have been very often looking at it. Can we control the trajectories of a differential equation to reach a desired target? It's very important question in applications. Or can we control it in an optimal manner? That is also very important. Can we use this to control, use the control to stabilize the system if it is unstable? So very often we would like to stabilize the ship or the moving vehicle because there will be vibrations. So these are all practically very important questions. Now for ODEs, these are very well studied. In the last few decades, these are being extended for the PDEs. So I'll try to explain a little bit about the flavor for the same questions in the PDE setup. Solutions of a system of differential equations in Rn is Z prime equal to A ZT, where now A is a matrix. This ZT is a trajectory evolving in the n-dimensional Euclidean space. Now it's starting near the equilibrium point 0. The solutions will tend exponentially to 0 as t tends to infinity if the real part of the spectrum of A, sigma of A, I'm denoting the spectrum of A, that is the eigenvalues of A. So if the real part of all the eigenvalues of A are negative, then I know the matrix A is stable. All the trajectories will go to 0 at as time goes to infinity. But what happens if again it got stuck, I think. Okay, I can move from the computer. Huh? Yeah, it came to the next one. Yeah, it's moving, Yeah. Thank you. So suppose the matrix is not a stable one. It has some bad eigenvalues on the positive complex plane. Then I know some trajectories can blow up to infinity. So in such a case, we can add a control term to bring the trajectories to 0. So the control operator B is given to us. That will be another n by m matrix. What is to be found is the control U. That is, let us say, is an m vector that is to be determined. Now, such a control in a feedback form, that means which depends on the state of the system ZT, and this K is a linear operator from Rn to Rm. So if you can get it in the feedback form, and that can steer the solution to 0. This we know how to construct in the case of the ordinary differential equation. It's well studied. And this system, that is Z prime equal to A plus BK of ZT, is going to be stable because all the eigenvalues of A plus BK are in the left half of the complex plane. So the system becomes stable. So the choice of this K matrix is crucial. It is called pole placing. That is, you shift all the positive eigenvalues to the negative half plane. Okay. Now the choice of such a linear operator K is well understood for ODEs. Now how do we do it for the PDEs? So let me talk about stabilization. Now we want to extend these techniques to PDEs. So we would like to view the PDE as an ODE evolving in an infinite dimensional space, usually the function space. We rewrite it as it could be a function space of a suitable Sobolev space, or we rewrite it as an operator equation for dut by dt equal to aut, except that this ut is no more a trajectory in the Rn, but it's a trajectory evolving in some Hilbert space of functions Z. And so this A is no more a matrix, n by n matrix, but it's going to be an unbounded operator with a domain in dA. Usually that will be a differential operator. It could be d by dx, d square by dx, involving different derivatives. So that is why it is not defined in the whole of the function space. If they are just L2 functions, you cannot take the derivative, but there will be a smaller domain in which the operator will be defined, but you would be able to show it generates a C0 semigroup ST on Z, which has the similar properties like you saw in ODEs. And then with that, if we can do a little bit of spectral analysis of A in that infinite dimensional space, then we are able to construct feedback operator to stabilize the equation. So this is the idea in extension to the PDE case. So we tried it, how we tried it was, as you know, Navier-Stokes equation was a nonlinear equation. You cannot directly go to handle that. So we will linearize the system around constant steady state. So the nonlinear terms will become linear again. Then we can try to we put it in that operator form as a linear equation evolving in a suitable function space, and then carry out the spectral analysis. If we can find out basis of eigenvectors, it's all the more better. We can say many things and analyze the interior and boundary null controllability. That means, are you able to drive the trajectory to the 0 state? That is null controllability by using control in the interior or control in the boundary. So that is the question. Or approximate controllability. That is, if you cannot reach 0, at least you will remain close to 0. within some epsilon ball. Or you construct a feedback control to stabilize the linearized system like we did in the ODE case. Can we do that? And once you do that for the linearized system, the same feedback control can be plugged into the nonlinear system, and you try to do a fixed point iteration and hope that will work to locally stabilize the nonlinear system. This is the broad outline of how a PDE stabilization works. So what we tried to do was we started with compressible Navier-Stokes system and linearized it around constant steady state, and we could get find the basis of eigenfunctions. And then we explored when it is interior null controllable or boundary null controllable, all these questions we could settle. And when it is not null controllable, the system is badly behaved, then the question becomes relevant. At least can you stabilize? The difference between this is null control, you are asking in finite time, you should reach zero, which may not happen very often. Whereas in stabilization, you are asking as t goes to infinity, can it at least reach zero? So that is practically more relevant, and that we could prove for the linearized system for the locals, using that local stabilization of the nonlinear system through this feedback control, what we computed. Now then we took up the Boussinesq system and the local stabilizer. These are heat conducting fluids, what we considered. Then we tried to do local stabilization, and the interesting point is we wanted to check it whether it is numerically, we can test it. So with the colleague who did the numerical implementation, we could see that it was working very well, and the solution was decaying fast enough. Now, considering the incompressible Navier-Stokes, we wanted to study the periodic solution because it's practically very relevant, because the blood flow is almost periodic, and we wanted to stabilize such a system, thinking that later on we could think of blood flow models and consider such stabilization questions. So that worked also after some difficulties, because the periodic solution case is slightly different in analysis. Then we were looking at viscoelastic fluids. It's a different system, so we could only study controllability and for the linearized viscoelastic fluids. Now we are all these we tried with the linear system was with constant coefficients, so it was easy to compute the spectrum, eigenfunctions, all this. But it's more difficult with variable coefficients. We can't write down the eigenvalues and spectrum, but we are trying in some cases, if we can say something about the presence of essential spectrum or the discrete spectrum, and can we say something? So that is what is the current work and we are doing. So let me introduce to you my collaborators, and Jean-Pierre Rameau from Toulouse, Michael Renardi from Virginia Tech, Sharka Nechesova is in Czech Academy, Prague, Anya is in University of Würzburg, and my former students Shirshendu Chaudhary, Debayan Maiti and Debanjana Mitra and Arnab Roy, all are now faculty, except Arnab Roy, who is Humboldt Fellow in Germany. And our this is over several years we were doing with all these students, and currently it's still continuing. And our financial support came from Indo-French, CEFIPRA Indo-French Center, and another Indo-French Center for Applied Mathematics, and also Airbus chair funds from Airbus offered to TIFR CAP. So I give you a little glimpse of some of the papers, recent ones. This was on the periodic solution stabilization. This was on the numerical implementation of Boussinesq. This was on viscoelastic fluid, and this was the compressible fluid in moving in, several bodies moving in compressible fluid with mixed boundary conditions. So maybe this is the time to stop without going into great details. Thank you for your patience.
Thank you very much. Thank you. We have some questions, please. Yeah. There are
IIT Jaipur. Ma'am, in the first slide,
Yeah,
you tell about divergence free velocity.
yeah.
That means you tells about incompressible fluid flow.
Yes.
Ma'am, what happened when we consider compressible fluid flow?
The velocity will be varying, and so I add an equation for so the divergence condition drops. Okay, so the divergence is no more zero. So without that, I'll have the same equation. I haven't written the equation. I think I'll have the same.
Ma'am, in that case, the density will not constant.
No, correct. Density is evolving.
Involving.
That is what I have written. I think in the first description. You see.
I think we consider Navier-Stokes equation in that case.
Yeah. That is the velocity equation is same, but density is no more constant. It's evolving. It could be evolving with velocity. So it's a coupled system of equation for velocity and equation for density. Like the one in the morning you saw, right? For Businesque, there was a coupled system where velocity and density were varying, right?
Okay,
it's similar.
Thank you, ma'am.
Purvi from Kathmandu University. I have a simple question. Like when we have to integrate some function and its integration is not possible, we use Monte Carlo simulation in the computer through numerical and we do a Monte Carlo simulation and we find the area by simulating numbers.
Yeah.
Is there any provision to solve the PDEs through this Monte Carlo simulation? If we don't get solution by normal methods, is there any provision?
You can. The numerical scheme, first of all, you have to approximate, because now the solutions depend on X and T. So if you could use finite element method or finite volume method or finite difference. So what you do is you suppose or spectral method. So one method, let's take, you write U as in terms of the basis functions, and the coefficients could be evolving in time. And so you write d by dt for the coefficients, and the the basis functions will integrate out. That is, you will get a mass matrix as a coefficient. So you get an ODE, which can be solved by standard Runge-Kutta or Euler scheme, or there are many schemes to solve that. So these are some of the standard techniques to solve the problem.
But these techniques don't work well in this situation.
They do, because only thing is you have to also complicate the other complication is divergence free elements you have to choose, but it's well studied. I'm not an expert in numerical analysis, but I have worked with somebody who.
Thank you.
Hello, ma'am.
Yeah.
Hi, ma'am. Thank you so much for the talk. In the slide 12, you explain, you use the word slip condition and interface condition. Can you please explain?
The slip condition is like Neumann condition. The U dot, they can slip along the interface. So when the solid is moving along the fluid, I have to prescribe something across the interface, right? The solid where it meets the fluid, some conditions must be prescribed. The usual one is the velocity of the solid and the velocity of the fluid is the same. That is like a Dirichlet boundary condition. You're fixing the velocity. You can also put in Neumann type of conditions. That is what we have, I called Navier slip condition. So only the normal velocities are continuous across the boundary, but the tangential velocities need not be. So you have to describe how they are both. So that is what I meant. Slip condition is like the body is allowed to slip along the fluid.
Okay. So you said that we will get weak solution in the sublow space. So is
Yeah,
it,
weak solution in a sublow space.
is it in H1 only, or
Sorry?
is it in H1 only, or some other complicated sublow
It's a
space?
very, yeah, you have to, because in the body it will be something, in the fluid it will be something, and they will match across the boundary only in the normal component. So
Okay.
it will not be overall H1. Because overall H1 will demand the function to be continuous.
Yeah.
It may not be continuous.
Okay.
So there may be a discontinuity across the boundary. So it will be partly H1 within the solid, partly H1 in the fluid part, but across they will match through the normal component.
Thank you so much.
Hello, ma'am. Thank you for the interesting talk. Actually, I don't deal with controls, but I'm curious to know where you were solving one system Z dash T equal to AZ,
Yeah.
and you were able to find out a feedback form of U of T.
Yeah.
So is it?
I mean, it's
feedback?
well known in the ODE. Engineers have been doing it for half a century. So it's well known.
Okay, so
What they do is they call it pole placing. Okay.
Mhm.
So what they do is, given the eigenvalues of A, so let's say some 3 of them are on the wrong side, positive eigenvalues, and the rest are all already negative. So they know how to shift the 3 of them also to the left-hand side. So this is, they do it via an optimal control problem. So you write down a suitable optimal control functional, and then when you, for the optimal control to exist, there will be a condition, optimality condition you can write down. And that when you analyze, there is an algebraic Riccati equation which will come out. And that equation gives you this particular K. The solution of that operator, the algebraic Riccati equation, will have a matrix solution. If I call it P, this K will be B transpose that P. So that is well understood in the case of ordinary differential equation. But for the PDE, it doesn't work for all the types of PDEs. But for compressible Navier-Stokes, linearized, when I write it as a system, we are able to imitate this and write down a Riccati.
So means in every ODE, we are able to find out such a kind of UT?
Depends on A and B. That A and B, if they are a nice pair, that is called Kalman rank condition. If that condition is satisfied, yes, you can. It can be controlled or it can be stabilized. You can push the poles wherever you decide. I want to put them far away beyond -20. You can do that.
Okay.
You will find a K suitably.
Okay. Thank you.
Can you take one last question?
Yes.
Sorry.
Yes.
Sorry,
Many questions.
So, if you are there examples of integrable systems where there is blow up, but you put a control and it still remains integrable? Is it possible?
Yeah, somebody asked me about this, but I have not worked with such.
But what about that Bussinesque?
Bussinesque was it's a Navier-Stokes, like in the morning, it was not
Not an integrable system.
Yeah.
Oh.
But it may be some people are working on integrable systems. So I don't know after control what happens.
Yeah, if it still remains integrable or not.
That's
Okay.
I don't know the answer. I'll find out and let you.
Okay, great. Thank you.
Okay, many questions. It's very interesting. So thanks again as a speaker.
Thank you.
Thank you very much.
Thank you.